Hello, we are the battery cycler team. This will be our presentation for our senior design project, battery cycler. So what is a battery cycler? A battery cycler is a device used by many industries to test batteries. How they test batteries is by charging and discharging the battery constantly to test for its efficiency and life expectancy. It does this through a charger and a load. The charger will charge the battery, load will discharge the battery, and this process will cycle in through until the battery is completely dead. So our requirements, we are operating at a voltage range from 2 to 4.1 volts, charge and discharge current up to 5 amps with a zero point 0.1 amp accuracy. Our battery cycler will have an output display with real time and battery voltage, current capacity and state of charge. It will operate off of the wall at 120 volt AC, support multiple battery chemistries, and for our self constraints, we will be limiting ourselves to a 12-inch and 12-inch dimension.
Here is the block diagram for the battery cycler project. We first start with the AC input, which comes for the wall, the 120 volts AC. We're using an AC to DC converter in order to power the rest of our devices, which are going to be from 12 volts DC, that being the microcontroller, the DC to DC charger, and the programmable load for the constant current discharge. As you can see from the microcontroller, it will provide 5 volts power to all the external components, such as the user display and the other components that we'll talk about later on in order to actually control those said circuits. These devices will also be communicating with one another through a control signal, which you can see in green, and this will all be used in order to create a successful project. Here are the project roles. First up is myself, Gustavo. Castillo. I was primarily in charge of creating the DC to DC charger. That included simulating the component as well as creating a PCB for it, and then eventually actually testing it in order to prove its success in our project. Gustavo had a similar role, this time on the programmable load side of things. In order to use a constant current to discharge a battery, he went through the simulations, PCBing, and of course testing. Omolloh was here for system support, aided in things like reflow soldering the boards that were to be tested. And then we also have Linzy, who was the primary control and software designer, meaning he was the one that was coding with the Arduino and ensuring that all our components could actually communicate with one another in order to create a successful project.
So battery characteristics, our main focus is the battery's capacity, or the total amount of charge a battery can store, measured in amp hours. We are achieving this by using a constant current load. With a constant current load, we are able to measure out a constant current, and with a constant current, we can simply document the time and ultimately measure for the battery's capacity. Other stuff like the cutoff voltage, C rate, and cycle life can be found through other processes.
So moving on to voltage curve and battery chemistry. So one of our project requirements is to have a user-defined voltage limit between 2.0 volts and 4.1 volts. With this in mind, we did some research to see the different chemistries of how much we can charge and discharge the different chemistries. So with nickel metal hydride, we found that the nominal voltage is about 1.2 volts. For the lithium ion is about 3.7 volts, and for the lithium iron phosphate is about 3.2 volts. So by knowing just how much we can charge and discharge the different chemistries, the team was able to test safely, and so that we don't overcharge or over discharge any of these batteries. Next, we have battery characterization. So with this chart here, we have a few different battery chemistries, and we can observe the different energy densities, life cycles, and total charging time. And from looking here, we can see that the lithium iron and the lithium iron phosphate are the most efficient for charging. They have the most life cycles, so they can be charged and discharged many times before they start to lose capacity. And then also the charging time is not as long as, for example, the lead acid or the nickel metal hydride batteries. So with our project, we also have to look at some safety concerns. So as mentioned earlier, we want to make sure that we're not overcharging, over discharging, or causing any type of safety concern or fire or anything of that sort. So just making sure we're not charging over the maximum capacity or maximum rating for the batteries, or we're not discharging past the cutoff voltage, or making sure that we're just observing and keeping ourselves safe while we test these batteries. Following up on safety, we can look at a few relevant standards that we applied to our project. So as you can see here, on the middle column, we have a list of a few different safety standards that we observed. Specifically for charging, we had to make sure that we're not charging past the fully charged voltage level, preventing thermal runaway, which is when the battery starts to self-heat, making sure we're not discharging past the recommended discharge cutoff voltage, and then also making sure that we're operating the batteries at a safe temperature level. So then now I'll just quickly go over how we actually applied the safety standards to our project. So with the first standard is the IEC 62133 standard. So this is for having precise control of voltage and current that we apply to the battery. And how we did this is by having our constant current load and our constant current, constant voltage charger. And then next is the IPC 2221 standard. And this we applied this by using 100 mil trace for the 5 amps that we use for our PCB design. And then for the IEC 60950 and UL 6236A1 standard, this was for our power supply. And this is actually how we ended up choosing a certified power supply instead of making our own. This way we minimize any type of risk for electric shock or fire. And then for the IPC A620 standard, this is for choosing the proper wire gauge for battery connections because we're using up to 5 amps. So we needed at least 14 AWG for the wires and to have secure screw terminal connections. Then lastly, we have the IPC 9592 standard, which is for power conversion devices. So making sure we had heat sinks that were sized based on the MOSFETs for charging and discharging. This way we can avoid any thermal overload.
Now we will get into the development of the DC to DC charger. When it comes to batteries, there are many different charging methods you can choose. In this project, we primarily stuck with the CCCV, or constant current, constant voltage charging method, which you can see in the figure here. The first step, you have a constant current that's flowing into the battery, and that goes until the battery reaches its upper target voltage, which you will see in a datasheet. That's primarily the voltage you don't want the battery to go over, or you risk doing harmful things such as overcharging, as well as batteries actually swelling up or even catching fire. So that's why you switch over to the constant voltage point once you get to around the 80% charge. And at this point, the current slowly drops off until the battery reaches its full charge, and this will conclude the constant voltage method to fully charge the battery. Here's our solution in order to achieve the constant current, constant voltage method in our project. This is the LTM8026 constant current, constant voltage step-down regulator, which is essentially a buck converter, which you can see inside the figure. A synchronous buck converter, meaning it has two MOSFETs that are switching on and off in order to control the duty cycle of the buck converter in order to get the appropriate voltage or current output. So that's what it is. You have a higher input going to a lower output, but you have voltage and current control through the current mode controller internal to the device. The device is rated for inputs rated from 6 volts to 36 volts, output 1.2 to 24 volts. And here's the key: output current up to 5 amps. As we mentioned, the output voltage and current is controllable using the external pins, which are connected to that current mode controller. And this is what we will be using in order to achieve that method. Here's the LT SPICE circuit for our constant current, constant voltage charger. We're using the LTM8026 model in order to simulate the constant current, constant voltage output behavior of this device. In order to control the current, we are sending a voltage to the CTLI pin, a voltage of 0 to 1.5 volts, where 1.5 volts corresponds to around 5.6 amps out of the circuit. In the real world, this can be achieved using a DAC, or digital to analog converter, and a voltage divider in order to scale down that voltage accordingly. So now you have precise control over the voltage being sent there, and now you have control over the current. The other thing that we can change here is the voltage control, is by changing the resistance tied to ground to the ADJ pin. You can see on the upper half of the screen what each resistance corresponds to the output voltage. This has been tested, so we know that this is how you can actually control the voltage out of this device. What you see on the right hand side of the screen is the pre-charge circuit. What this means is it provides a pre-charge path for the battery to charge in case the battery voltage is too low. You don't want to send a really high current to it right away. To achieve this, we're using two P-channel MOSFETs, also known as a PMOS, in the high side configuration, such that they can be logically driven through a microcontroller easily without the need of any external gate driver. And this is what we will be working with. Here's the output result from our LT SPICE simulation for the LTM8026 charger. As you can see, the graph strongly resembles the theoretical method that we showed earlier for the constant current, constant voltage charging method. In this setup, we have 5 amps constant current and 4.1 volts constant voltage, which are corresponding to our maximum requirements for this project. The way this was achieved in the simulation was we sent 1.32 volts to that pin, the CTLI pin, through a DAC, which was sending 4.44 volts, which again we mentioned was for the divider. In order to achieve that constant voltage, 4.1 volts, we just set a resistor of 4.18 kilo ohms. What you see down here are two equations that we can use from the simulation in order to achieve any current output or any voltage output. All we have to do is either change the DAC voltage for the current or change the resistance for the output voltage. Following the successful LT SPICE simulations, we went ahead and went on to create a PCB design for this charger. The first iteration you can see on the left-hand side of the screen. This is just a translation of the LT SPICE circuit, which you saw earlier. The way that we created this exact PCB was through the datasheet recommendations, that being using large pores for different traces such as the output voltage. We ensured that it was thick enough to handle the 5 amp that could be sent into the battery. The ground pores were big enough so that they weren't split apart, and to ensure that the entire board had a solid ground connection. You can also see the footprint size of the LTM8026 chip, which is in the middle. It is a BGA81 chip, which was quite difficult to solder. However, we did get it working in the end through reflow soldering through an oven. The second iteration you can see on the right-hand side of the screen is largely similar to the one on the left, except it's a bit bigger, only to include space for the heat sinks for the MOSFETs, which was something that we overlooked, which is important in cases if you actually go to 5 amps, that could lead to really high power dissipation, and the heat sinks are a better way to manage that. So this is what we have for our PCBs. Here you can see the final product of the LTM8026 constant current, constant voltage charger that we soldered. This is actually the second iteration, which we mentioned had the heat sinks on there. Here we have everything hooked up, and you can see the different outputs that we got. First off, on the bottom left side of the screen, we can see our current control. We compared the LT Spice results to the measured values, so we can see that actually changing that voltage sent into the CTLI pin indeed did change the current behavior of the LTM8026. It's not one-to-one mapping, however, you can see as you increase the voltage, the current increases as well. So that worked out pretty well. What you see on the right side of the screen is for the charging voltage control, which we mentioned was changing the resistance at the ADJ pin. The LT Spice simulation data is on the left, the measured values are on the right. We could see that, again, the resistance don't match up quite exactly as they did in the LT Spice, but you can see that changing the resistance indeed did change the output voltage of the charger, thus indicating that this PCB was a success. Now we will look at the programmable load development.
So what is a programmable load? Programmable load will be a main component of our battery cycler. It is an instrument that will offer various control. Our main focus for the programmable load is the constant current. As I mentioned previously, we are wanting a constant current to simply measure, document time, and measure for the capacity, as capacity is current times time. This is our LT Spice simulation. We are operating with IRLZ44N MOSFETs, TLV9152 op-amp. The op-amp, the MOSFETs will be operating in a linear region and allow for the programmable load to vary its resistance to output a constant current load from the drain. We were simulating an input of ranging from 10 to 100 millivolts. This will be from the Arduino, and our control to measure for the amount of drain current, and this divided by the shunt resistor at 20 milliohms will output our desired drain current. These are our simulation results. As you can see, we are measuring from between 2 to 4.1 volts. The red line represents the drain current, and the blue lines represents the different battery voltages. So with a programmable load, as the battery voltage changes, we are wanting the current to remain constant as per a constant current load. So before we are actually building our device, we had to calculate for potential temperature issues. So as we with a single MOSFET and no heat sinks, we determined that it was ranging up to 1,265 Celsius, which is kind of ridiculous. Might have some errors with the formula, but we just knew it was going to be really, really hot. So we determined through this through calculations that 4 MOSFETs with heat sinks will output a temperature of around 52.3 degrees Celsius. This is our breadboard testing results. The breadboard testing was at thousandths to a scale. Before we go to actual testing, we were simply trying to measure out for a constant current. So as you can see, with the input, we produced quite close to our expected output as our measured simulation output. We're measuring this as a constant current controlled by the Arduino, and we also measured for an accurate constant current behavior as we changed the battery voltage or our drain voltage. We were able to measure out for a constant current. So after our breadboard testing, we went into PCB design. We used EasyEDA to design our initial PCBs, which didn't work out as we wanted. We were missing some via connections, and this was just simple mistakes from just not understanding EasyEDA enough. This led into our final PCB design, which was improved with trace widths and copper grounding planes. We had the help of the Pulse Power Lab to purchase and deliver our PCB boards. This is our first version 1 PCB load. The resistors and capacitors were soldered on through a stencil and heat gun. On the image on the left is the PCB without anything equipped, and the image on the right is the heat sinks equipped with the Phoenix contacts. The MOSFETs were also super glued onto the board.
Oh! That's why.
So it isn't a project without some errors and some hazardous happenings. Some mistakes were made as we tried to, when initial solderings, we put our initial resistors and solder paste onto our board. We tried to use the lab refill oven. Unfortunately, the board was too big and it covered a thermistor, I believe, and caused the oven to overheat. So this is our updated final PCB design. We realized that our initial one had a missing via connection. This prevented a connection between the bottom and top layer at R2. I updated new shapes, new connections of the board to basically give us options on how we want our design to be. This is one of our updated PCB designs. It's a longer shape. I just liked it because it was linear and more simple and easy to look at. This is our measured constant current at 4.1 volts. The measured drain current, as you can see, at different Arduino voltages compared to our expected drain current from our simulations. As you can see from the graph on the right, the drain current at 4.1 volts is linear. However, we have some issue with the range of the slope of the drain current. As we mentioned previously, the drain current is measured by the input Arduino, ranging from 10 to 100 millivolts, and the shunt resistor at 20 milliohms. So expectedly, we believe that at 100 millivolts, the Arduino should output 5 amps. However, as you can see, we had to push the Arduino voltage to meet that 5 amp mark. Now, we do not know the specific reason, but we do believe it may be because the MOSFETs are currently not at fully activated in the linear region, and the gate voltage might be lacking. So we might have to supply the Arduino with more voltage and maybe replace the shunt resistor to compensate. This is the same measurement, but at a battery voltage at 2 volts. As you can see, the measurements, the drain current remains the same and the graph remains unchanged. However, the previously mentioned slide still applies. We are still unsure of why the range of the Arduino is extended. It could be a multitude of reasons. We're still not sure.
The purpose of the bidirectional switch in this project was in order to switch between charging and discharging easily through the microcontroller. That means we should be able to either turn on the charge path or the discharge path by sending a control voltage from an Arduino. What you see here is you have two sides. Left side is the charging, right side is the load for the discharging. In each of these paths you had a NMOS back-to-back connected, source-to-source connected MOSFETs in order to fully block the current from passing through either path. These were driven by an LTC7001 gate driver, which was the one that was actually going to the Arduino or microcontroller in order to change the voltage to turn on that path. Here's the PCB we ended up creating for the bidirectional switch. As you can see, the design mainly features the two components that we see. The right side you see the gate drivers, as well as terminal blocks in order to make the connections easily. You can see our MOSFETs had all the heatsinks put in place because of, again, you had the 5 amp limit that our project has. However, we were unable to actually get promising results with this PCB, and thus we decided to focus on the other components that needed our attention, and that is why we had to sadly move on from this piece. Now we will look at the software and control components for the battery cycler project.
There's not much to say here. The Arduino Uno was more than capable of handling all the tasks the battery cycler was going to need to be able to handle, and it handled it with flying colors.
One of the project requirements was to power the project completely from 120 volts AC, that being what we all know as the wall outlet power. Our power supply needs in this project were as follows. First was the constant current, constant voltage charger. Second was the constant current discharging through the op amp. And third is our microcontroller, which is the Arduino. We found that these three components could all be powered off 12 volts DC, thus we decided to use the AC adapter that you can see on the right. This takes in 120 volts AC and outputs 12 volts DC with a 3 amp DC limit. In order to achieve this easily in our project, we're using a DC barrel jack splitter in order to distribute it to the three components here. Because an Arduino can either send a logic low of 0 volts or a logic high of 5 volts and no in between, we needed another device in order to send any voltage between that range. This is where a digital to analog converter comes in. The DAC that we used in this project is the MCP4725. We used one for charging and one for discharging. In order to distinguish the two, we changed the address, the I2C address of them. One of them being OX60, the other one being OX61. That way the Arduino knows which one to talk to. The MCP4725 offers 12-bit resolution, meaning 4095 discrete steps. As we mentioned, it is Arduino compatible, and in the charging case, we're using it in order to send 0 to 1.5 volts for the current control pin, or for the load case, we're using it to send 0 to 100 millivolts, or in reality 130 millivolts for our actual project on the PCB in order to control the constant current discharging. Here you can see a little test I ran just to make sure we can use both DACs on the same bus, by making sure that we had a different address set to the two. What you see marked as a CTLI is the charger current control pin, which we're sending 0 to 1.5 volts. On the right side, we see the load current control, which we're setting 0 to 100 millivolts in this case. You can see we're using a divider in order to achieve that voltage, which makes it easy for us to control through our display. Here are the results for that DAC test. Let's start with the charger current control. you can see the orange part is what we have control over, which is the DAC voltage. The blue part is what is being actually supplied into the current control pin, that being through the voltage divider. And the green part is the output current that is achieved through this control. On the right side of the screen, you see the load current control. Again, we have the DAC voltage marked in orange. What is the corresponding voltage that is actually being set into the op amp is in blue, which is our control voltage, and the actual discharge current is marked in green. Thus, we can prove that these DACs can work in order to change the current behavior in both circuits.
Here are the lab test results of actually controlling the discharge circuit with the DAC. As you can see, we plotted out every last value that we would want for our output and the level of control and accuracy that we would want, and we recorded each bit value and what voltage we set the DAC to, so that way it would be easy to implement this straight into the code for the battery cycler. To control the voltage output of the charging circuit /LTM8026, we need to put a varying resistance on the 80J pin. And the best way to do that is through a digital potentiometer. That way we can set the output voltage through a user input like this screen, and the potentiometer would vary its resistance in order to vary the output respectively based on what the user selects. The one we went with was the 805252, and although it went up to 50k ohms, which is more than what we needed, it offered enough resolution and it communicated through I2C such that we could implement this to our design seamlessly. Here we have the test results of just hooking this up to an equivalent circuit to test if we could actually control the potentiometer and that it worked properly. Here are the lab test results of implementing the digital potentiometer with the charging circuit. We were able to successfully control the voltage output by varying the resistance, and we were able to do all of this just from the user interface, such that we didn't need a laptop to go into the command terminal and change the resistance of the digital potentiometer manually. We were able to just do it through the screen, all while powering it from the wall. Early in our project development, we talked about using a sensor to monitor real live time current and voltage of our batteries as we charge and discharge them. For that, we selected the INA260. Later in the slides, you'll see that we did get around to implementing this into our final design so that we could monitor the real-time power of the batteries as we charge and discharge them, and it worked phenomenally. Here we can see the display attached to the final product of our battery cycler working as designed and as expected. Here's a picture of our LCD display working seamlessly with all our other components on our final battery cycler product, and you can use the buttons to navigate through the menus and change the battery voltages and currents on your batteries as you charge them or discharge them all in real time. Here are some pictures of our final working battery cycler design. As you can see, there is a battery hooked up to the charging side, currently charging. And now for a demonstration.
Okay, so here you can choose either charge or discharge. Let's say we go with charge. At that point, once you select it, it's going to make it to where the other side of the battery cycler doesn't turn on, right? So we can charge up to, between 2 and 4.1 volts. So let's just go up to 4.1 because we're charging a lithium ion over here. And then let's say we want to charge it at, let's see, 0.2, right? You got that reading there? So we can see it. We can actively change it. As we change it on the screen here, see we got 0.3, 0.4. It'll change right there. And then when we click select and we confirm that, the final screen is going to show us what we're seeing on charge and discharge. Now discharge, you're not reading anything because it shouldn't be, but here you can see that's the battery voltage here, and it's charging at the 0.4 that we wanted. We can go back through the menu. Let's say we wanted to go to discharge now. Let's say we move the battery over. You click on discharge, and it should set the current down to minimal amount. This is what you're seeing from the battery as it goes the other way, so that's why you're not seeing anything. We want it to cut off at 3 volts, and let's say we want to discharge at 0.3. So if you look here, as we change it on the screen, right, you can see 0.3. As we go up to 0.4, 0.5, we can change it here. You click that, right, confirm, and go to the next screen, and then it's going to show you what you put it at, right, as you discharge. And then if we start decreasing like the battery's voltage here, like if we add an actual battery here, and it goes down to that cutoff range where I said I wanted to kick off, it'll kick off and stop drawing any current off of there. So as you can see, you can also see it here on the screen, it's not drawing off any current.
We've come a very long way. After many months of hard work, we have successfully completed our design almost. As you can see, every task that we set out to do, we finished except for the capacity tracking algorithm. We had some minor setbacks, but in the end, we got most of it done. The only thing left that could have been done was the capacity tracking algorithm of the battery as you charge or discharge it. Right now, it shows you the live currents and voltage values of the battery as you charge or discharge it. But there isn't a capacity tracking algorithm currently that shows you the percentage of the battery's charge. Maybe with a little bit more time, we could have implemented that. But as of right now, as it stands, got everything else done. So we're all pretty happy about that.